So I'm Johannes Münchmeyer. I'm currently a postdoc at the GFZ, and last year worked with Frederick on a project linked to SUBMERSE, which was about phase-picking dust records. So this is about earthquakes and dust records. And it's about a picker called DeepSubDAS that I didn't develop, but Han Shao, who's a different postdoc of Frederick, who unfortunately can't be here today. So I'm presenting Han's work, and then what I did is integrating this into a library called SeisBench. Um, For the general agenda, I'll give you a very brief run through of what phase picking with deep learning generally is, how it works in classical data, and then show you a bit what can be done on DAS, both in terms of using the classical three-component seismometer models on DAS, and then on DAS native models that are native to DAS data. And in the end, we'll do a practical where, like a notebook, like Afonso just showed. Um, so for the people who might not be seismologists, what is phase picking? Phase picking is if we have a waveform like that and we see there's clearly something happening, there's actually a P arrival and an S arrival in here, is the process of identifying that there is a P arrival on S arrival and identifying at which exact time this happens. And the reason we do this is because this is the first step to earthquake detection and to basically all downstream characterization of earthquakes. So this is an elementary task for earthquake monitoring. And we need to do this at scale because you'll have millions of phases in a seismically active region per year. So by eye, it's fairly easy, but it needs to be automated. Now, the very fundamental idea of detecting earthquakes with deep learning of phases is essentially you take a lot of examples that are either earthquake or noise, you feed it through a neural network, so essentially just some layers of linear algebra, and you check if the output is correct. And depending if it's correct or wrong, you'll adjust your network, which means your coefficients in this linear algebra. So it's the super high level view of deep learning for earthquake detection. If we go into the slightly less high level, what do we actually do on a standard three-component seismogram? So this figure is from the FaceNet paper, which is the most common, or like I would say the most prominent seismic phase picker. You can see we have these three-component waveforms, and the trick is what we do, we model the phase detection as a sequence labeling. So we produce a curve that says with what likelihood is there a P wave here or an S wave here, and we train them to give us these triangles, sometimes Gaussian pulses. So we give it some pulse. Essentially, for every sample, we output a probability. So this is what happens. You label the sequence, and once you have the sequence at the bottom, you just look at the peaks of these probability curves, and these are the timings of your phases. And also, if there's a peak at all, that means there's a phase. That has proven to be quite a versatile model. That's more or less the standard for regular seismic data nowadays. Now, a bit of detail for the people who've heard a little more deep learning. What is FaceNet actually? FaceNet is a UNet, which means it uses convolution. So this left branch is convolution, providing a very compressed representation of this whole input, which is 30 seconds. And then it has these transposed convolutions, up convolutions, however you want to call them, to map this back to the original lengths. And you always have in between these gray arrows, which are called residual connections. This is just so that it can basically keep information at a lot of different scales or sampling rates as well. If you didn't get this slide, don't worry, it's not integral. So about 5 years ago, towards the end of my PhD, was early into the phase when all of these deep learning pickers came up. And there was a big problem that they all had different APIs and they weren't comparable. So we developed this toolbox called SeisBench, and SeisBench combined different aspects. We brought in different models that we all implemented into SeisBench. We brought in benchmark data sets, and we made sure that everything had a unified API, a standardized format, so everything is interoperable. And then we built this link in between for training. And to be fair, when we initially developed it, it was more planned as a benchmarking exercise, but it has developed a lot more into a toolbox for people actually wanting to apply these models. By now, there's quite a few outside contributions. So we now have, I think, 20 benchmark data sets, and the number might be outdated already. And 16 different models, a lot of phase picking, some denoising, dust picking, as I'll mention later, and more than 80 sets of pre-trained weights. So you can use it out of the box. And a good global user base for this project. Okay, So much for classical three-component data. Now, what do we do if we have a DAS record like this? Clearly, it's different. We don't have three components, but we have lots of channels. So the first thing we can do is we can say, well, let's extract a single channel, then triplicate it because we need three components for the model as input, give it to FaceNet, get our probability curve. So this is now the P probability. This is actually the P probability FaceNet gave for that trace, which is somewhere in the middle of the record. And now if we do this for all channels, we can get picking results. And in this specific example, it isn't even too bad. We get the P wave, we get the S wave. It's kind of hard to visually align it. But you see they're reasonable, even though they're not completely stable. There get a couple of jumps here and discontinuities, but overall, we get a reasonable result here already. The problem is this is clearly not optimal because it works, but we are missing out on the biggest advantage of a dust table, that it's spatially coherent. And that brings us to the question, how do we do that? Well, the first problem is we need a lot of data to train a deep learning model. And for classical data, over the last decades, analysts at all the centers have picked millions of faces, so they were readily available. For DAS, no one has done that. And what Han Chao did is first he collected these different data sets, 13 different fibers, about 92 million records combined. So if you count up the number of channels times the number of examples, at diverse locations and tectonic settings, shown here and on the top left on the map. Frederick knows a lot more about this data, in case you have questions. The problem is then that this is unlabeled data, and what Han did was essentially use the approach that I showed before. So he used the three-component pickers. So you see on the left, applied this, and then went over it by eye and said, okay, is this correct, or do I need to fix it? And manually reviewed all of these examples. So this is a semi-automated labeling scheme. To be fair, the labels aren't perfect that come out. Like you can look at them, and if you look at enough examples closely enough, you'll find issues. But it's a good first proxy of labeled data that was easier to create by using a system that gives you a rough approximation. And then once you have these manually reviewed examples on the right, you can actually train a model. And this is the architecture of DeepSubDAS. It's the so-called DeepLab version 3. So it's one of the famous convolutional networks. And it's essentially the same as the FaceNet was in 2D. In 1D, it's in 2D. It uses 2D convolutions to identify features that are not just along a channel, but spatially. So you get the data, and in the end, what we get out are these masks. So to show it in the figure, as in the figure before, we take the dust record. We don't actually do anything to it. We just feed it right away to our model, and we get our picking result, which in this case has very nice and continuous P curve and S curve. There's a couple of noise in here. I'll show this a little more in the training notebook that I'll show in a minute. But in principle, we get results. Now, what I did recently is that I added these models to SeisBench. So on one hand, I added a wrapper, which allows you to apply all of these three-component models to DAS. Then I added DeepSubDAS. And all of that builds on sort of a generic interface so that when there's a new model, you can just put it in and you automatically get the functionality to have this running. And all of it comes with GPU support. Underneath is XDAS, which is a library developed by the people from Azure, and we'll see this in action in the notebook as well. XDAS gives you, for example, the possibility to load DAS data files from many different, well, basically all the common interrogators directly. So all the I/O, for example, is handled through XDAS to be flexible. Okay, now let's go to the actual example. I'll just add the URL underneath here, and then I'll change myself. Okay, before I switch to the example, are there any questions? Stop share. Where do I find the Google Chrome? Oh, there we go. Yes.
where say big basin was to integrate basements, because usually it's improving the key rate, and we are getting some reasonable hits with the net. That's the situation.
You were integrating along the space axis. I don't know. That's probably a question Han would be better at answering, or maybe Frederick knows.
Yeah, so I think that we haven't tried that, but it's in principle meant to be like flexible for different cable geometries, etc. Right? So you need the straight cable sections. But then I agree that's something that should also be benchmarked against that.
Yeah, so you might need to close the other Colab notebook because Google doesn't allow you to have many Colabs running at the same time. So if this doesn't run, might run the other. I think I can, yes, English version. So before running this, I would recommend to go under runtime and change runtime type. It's also written in the hint up here because we want to run on a GPU. This is not a particularly great GPU, but it's free. And it definitely accelerates the processing. And you need to do it at the beginning because Google essentially resets your whole runtime the moment you do that. Okay, as before, we need to install the dependency. And because some of this is already published as a version with a version number, but not all of it, we are installing this from the repository directly of SeisBench, but it's in months from now, the latest this will be in the SeisBench, also the published version once it comes out. Okay, in terms of, yeah, let's wait a moment. We'll also ask to restart as before. So this, just to mention, we're installing the DAS capability because the access dependency and a couple of other dependencies are quite heavy. This is sort of an extra package that is added onto SeisBench, not just the standard SeisBench. Okay, done. Good. Let's import all the dependencies. So the really necessary dependencies are only the first two. The other two are just for visualization and some data handling that we're doing on top of it. We're using an example data file that is about 3 GB that's uploaded on a server. It's coming from Chile. So it's a DAS cable run by the people in Jersey, actually. And it contains an earthquake, as you'll see in a moment. Let's see, that should hopefully be a little faster. Okay, just so that I don't have to wait 4 minutes now while explaining, and because we anyhow see the outputs of the cells here, I'll walk through the notebook. You'll do it in your own time then. I think that's easier. So the first thing we do is we use XDAS. Now, I'm not an expert in XDAS, but as a general functionality, we can load data. This data array is in netcdf format. It's written by XDAS, so it's a native XDAS format, but we could also load most of the other interrogators, OptoDAS, IDAS, and we get the same object. And this is a data array, and we can see it has how many samples, how many channels we get. And what's noteworthy is this is a virtual source. So when you load data in XDAS, it actually just loads the header, essentially scans how much data is there. It doesn't load the actual data underneath it. This means this operation is very fast and very lightweight. The reason is DAS data is often larger than your memory, so we don't want to load the data. And what you can also see is XDAS takes care of the coordinates. So we have a time coordinate, we have a space coordinate. We can index this data now both using these coordinates or directly using the samples. So what does it look like? We can treat the data simply like it's a NumPy array. That's what we're doing here. And it's samples, then channels for this. So we say, let's take the data, select all samples, and 1 in every 50 channels. So it's channel 0, and then 50, 100, and so on. And plot it. And this is functionality of XDAS. And what we can see nicely is this here. And this is an earthquake locally in that region. And you see the first arrival here is a P wave. We'll zoom in a moment. There's actually 2 arrivals around the P. And the second arrival is an S-wave arriving at this cable. So visually good to see, and that's also good because it makes for a good example to test the model on in a moment. Now, what we can do is we can clearly also subselect a smaller range. So based on this, we can guess what channels would be interesting, what time, just visualization. And here we create a selected data. And this is this example. And here we can see more nicely the P and the S wave. If you look very closely, you might already spot that actually there's a P wave, and this is a sediment conversion, a P to S conversion, which is stronger than the original P wave. What happens internally is the moment I call plot is only the moment that Access is actually loading data. So it never loads the whole data into memory, but only the selected data that I want to. Everything else stays on disk. Now, let's start off with the 3 component models. The first thing we do is we need a base model, and we can load essentially everything that SeisBench has available. That is FaceNet, that's EQ Transformer, that would be GPD, but that would be extremely slow. And we can select what it should be trained on. And for example, here I say, load the model that is trained on the so-called DTing dataset. DTing is a dataset from China with several million hand-labeled face arrivals. It's a dataset that both the people at JSU actually and we have found to work surprisingly well when running on dust data. There are others that also work, but this is one particularly nice example. And now what we do is we say, okay, let's take our base model and wrap it to become a dust model. And we say component strategy is clone. That means exactly what I said. We take one dust channel and triplicate it as Z and an E channel of a 3-component seismometer. There's another strategy that's implemented that's called PET, which simply means PET with zeros. So take it just as one channel, fill the others with zeros, and that's what we get. Okay, now the data is loaded. I'll quickly run through the cells above just so I can show you the next cells live. Okay, so data loads. We can get the plot in real time. That takes a moment because it's quite some data still. We can select here. Oop. And now let's load the, not what I wanted. Load the model. And what you'll see here is it actually did a download, and that is it downloaded this FaceNet model because SeisBench has all of these model weights on a server. The first time you use them, it will download them, it will cache them locally. So now we have this model available. One thing, as I mentioned, is DAS is quite heavy, and it runs better if you run it on GPU. It actually doesn't just run on the typical Intel GPUs. You can also run it on the accelerators that all the Mac chips have nowadays, so the Apple Silicon. You can also run it on the Intel accelerators that are fairly recent. That's what I did on my laptop. That's why it says XPU. That's an Intel device, but if we run it now, it should hopefully say CUDA 0. So this means it runs on a NVIDIA CUDA device. That's why we had to change the runtime in the beginning. Okay. Now, one problem is if you do classical face picking, you would hope to get this whole probability curve out. But if you do DAS, then your input is just as big as your output, or even your output if you have P and S phase is twice as much as your input, because you'd get a whole probability map. That will quickly explode your memory. So what's better to do is to say, well, we anyhow need to process this patch by patch. So we go through the different patches, and every time we have a prediction for a patch, we'll handle this, we'll process this in some way. That might be write it to disk, that might be picking the faces, and then we throw away the patch. We get it out of the memory because it will be too big. And that's what we do through callback. So a callback is simply a function that is applied to each patch that the model predicted. Now, sort of anticlimactic, the callback we're using is a memory collection callback. So this will just keep everything in memory. That works because our input data is fairly small. If our input data would be huge, we couldn't use that, but for demo purpose, it's nice. Okay, we defined it. And now we can simply say model.annotate. There's a bit of a technical quirk here that's described above about async I/O. You can largely ignore this if you want the technical explanation. It's provided here. That's why there's an await, but you could do it just by writing model.annotate. And in 2 seconds, it has processed 8 patches, so that's what it had cut the model into. What do we get as a result? The result is an XDAS data array. So it's just an XDAS object as the one we loaded originally. So we have still our time samples, our space samples. We have coordinates when the time starts and ends. We have the spatial coordinates. All of that meta information is still retained. And all of the extra functionality, for example, plot. So we can simply say, results.plot. And it's probably slightly faint, well, doable, but we see we get our P probability curve, we get our S probability curve. You can see it's not quite continuous. It's not a perfect prediction, but it definitely corresponds pretty much with what we'd expect to see for P and S phases. Now, these probability maps are nice to look at, but if you wanted to do practical processing like phase association, what you probably want is you want discrete P and S times for each channel. And that's what we use a different callback for. The callback is unsurprisingly called the DAS picking callback. And because this is a standard use case, there's a convenience function called classify, which will do that. And we say here, okay, call something a P wave if it has at least probability 0.3. You see here on the scales, that's the probabilities. And for the S wave, we say same threshold. And then it does some clever deduplication to avoid that in one channel you have too many picks in a very short time frame, because realistically, picks need to have a minimum spacing. So let's run this. It takes, again, now in this case, 2 seconds. And we get an output, which might look a little messy, but essentially it consists of a lot of objects called DAS pick that have a time, they have a confidence, so that's the probability, they have a channel, they have a phase, and they have some attributes that are not set because they're optional. This is slightly messy to look at, but what we can do is we can just say, okay, let's create a pandas data frame directly from our output and sort the values by channel. And we get this nice data frame. And at this moment, we have all the functionality of pandas, so we could save this to a CSV file. We could filter it by criteria and so on. It's now a table. Do the same for the S waves. And we could concatenate this. So this is something that you could feed as an input to a phase associator to identify events, if you have the coordinates of the station, well, the channels. Okay. Now this is nice to look at, but let's do the actual validation and plot the original data and plot the phases on top. And well, now you can see it looks on the first glance pretty good. We see the P waves, we see the S waves, and they match pretty much the waveforms we expect, but you might spot a couple of aspects. The first is there's this wave and this wave, and this is exactly the direct P wave and the P to S converted sediment phase. And sometimes we pick the first, sometimes we pick the second. That is obviously a mistake, and that happens varies very much spatially because the model does not know spatial coherence. It looks at each channel individually. So a new channel can suddenly give you probability for the other of the two phase arrivals. It's also generally not particularly continuous. And something you see much better if I disable some picks and make them larger. Let's, for example, get rid of these and make the P picks larger. Is that we have plenty of channels where we believe that the S pick is a P pick. This is quite common, actually, as a mistake. It was a bit hidden when I plotted them on top of each other. So it's not perfect, but it's a good proxy, and we could probably, with good phase association, use this. Okay, this is for the wrapper. How do we use an actual DAS native model? Well, we simply load the model. This is the standard code, just that we now don't load a base model in a wrapper. We download the model, and you can see it's 200 megabytes, so that's about 100 times as big as the 3-component model. There's probably room to make much smaller models still that are good and more lightweight. And again, we move the model to a GPU, so it's now a CUDA device, which means all the compute will now happen on the GPU. Let's do exactly the same steps as before. We annotate. Will take a little longer, so it gives me time to explain this batch size parameter. So GPUs are good if they can do the same thing many times in parallel. So if you can give it many patches at once, GPUs are much faster. And essentially, this is controlled by the batch size. This says how many patches are processed at once. Clearly, the more patches you want to process, the more memory you need, especially GPU memory. So the T4 GPUs aren't particularly big. That's why I don't go for a big batch size. But if you have an A100 or something, or one of these 80 gigabyte video RAM GPUs in a server, you can put the batch size much higher and speed this up substantially. Okay, we see 16 seconds. We are done. Let's plot this. And coming any moment. And we see that the result is quite different. So before we had very discontinuous predictions, and now it's very smooth, very continuous across the channels. There is a false positive, so there is a false S detection here in the back of the signal. We could inspect the data and see if we figure out why this is, but we also see these very nice two real detections. And now what we can clearly do is we can say, okay, let's do the same, the classify, so use the picking callback and get the picks out of there. We can see visually here that the confidence value is quite high. So let's just set the thresholds also high at 0.9, so we don't get many spurious picks. And now this is running, and again, you can see such a model is much heavier. But in about 15 seconds should be done. The progress bar is not running linearly because we do this batching, so we'll get two results at once every time. Okay, now we're done. We get our picks with their time, confidence, and channel, phase, and I'll do this for the S wave. And let's just reproduce exactly the figure we had before. You can see, okay, there's our big false positive, which now suddenly is continuous. But what's quite nice to see is we have continuous lines for these picks, and we are continuously picking the actual first P arrival and not the P to S conversion for this event. This is now stable across all the channels and not a local artifact anymore, whether we see which. And this is because we are spatially coherent, because we pick in 3D and we produce, well, in 2D and we produce a 2D probability map and not one line at a time. Okay, this brings me to the last part, which I can launch, but probably not completely run. We were always just working on a small part of the data, and we are now used to the three-component model because it's a little lighter. And we load it and we put it on the device, all as before. And we open the whole data. And as I said, this is virtual source, which means the data isn't actually in memory. And our virtual source could also be 100 gigabyte, and that's definitely buffer memory. Now, what we can do is we can iterate over this data, process it, give it to a callback, evict the prediction, and continue. For example, we can do this and say, let's classify this and get picks for the whole data. I can run. Let's run the other one. But what's also interesting is we can say, okay, let's write the whole predictions, write the probability map to disk of what we're doing. And that's clearly also only something that you want to do if you have 100 gigabyte of disk space available. Or in this case, probably about 6 gigabyte, given that we have a 3 gigabyte input and we'll write a P and an S map that are both 3 gigabyte. But this will now run through the whole data, cycle it through the memory, GPU memory, discard, write the outputs like the moment it can assemble them and put them on the disk. And if we wait, well, as long as it takes on this T4 GPU, so I can probably guess roughly 5 times as long, so about 2.5 minutes, we can get the output. And then the output is, again, an XDAS array, netcdf files. Here we use a wildcard, and we use a function that is MF data, open MF data array. I think that's for multi-file data array. We open it, and we see that what comes out is a DAS array, an XDAS array. It has time coordinates, space coordinates, and we plot here every 50th channel, which contains, and this is the P wave, for example. Plotting every 50th channel is not optimal because we know that the results are quite different per channel, so it's not a good view, and we should probably do some deduplication. So, okay, a deduplication or anti-aliasing, but it in principle works, and we see that we now have a prediction curve for the whole data, just that when you go far enough away from the interrogator and also far enough from the earthquake source, then you can't really see the P waves anymore. They become faint, and there's a lot more confusion of P and S waves here in this part. Probably easier to see on your own screens than on the projector. Yes. And this way, you're able to cycle through basically data sets of any size, because you just only process a chunk and only have in memory what you need at this very moment. Yes. Okay, I'll keep this running. It will finish in half a minute, and I think we can all restart in questions.
Comment briefly on the question before. So the colleagues are not here, but today they did try to lots of integration. One of the data sets and yesterday they get for it.
Yeah, the video just disconnected.
Maybe we can turn it off now.
You can listen to the questions if you want.
Sorry.
Yeah.
Okay. Just a frame rate falling out. But it doesn't really matter because we anyhow, so they do it does an amplitude normalization. So the moment you don't, so for each window an amplitude normalization. So if we have a constant factor between phase and strain rate, it comes out at 0. So not well at 1, it's effective, but it doesn't have an impact. Let me quickly check. So it's definitely meters, but to be fair, it goes beyond 350. I've tinkered with the data a little bit, so I might have the channel spacing. Yeah, most likely I put the wrong channel spacing in the data because there was a problem with the original file. I had to reconstruct something. Probably the channel spacing should have been 5 and not 10 meters, and the cable is half as long. Yeah, no, this cable is not interrogated over 350 kilometers, definitely not. But half would be reasonable. It's a little under 200. Should be real. But that's, just to be clear, that's my error, not an Extus problem. I put the wrong data for Extus, and I didn't read it from the original file. Yeah, that is not a correct result.
On the previous notebook, there was a call out to the Royster, but we need to notify and ensure that the right station.
Yeah, but like Extus would do that if you load from the original file, which I didn't have for this example. Okay, now maybe just now last remark, now that it should have finished running, can see, well, I mean, we see what we had before, but now we have access to the whole P field, and we can also do this now for the S wave and say, okay, let's get the whole S wave, and we see it's a 3 gigabyte virtual stack again, and we can plot every 50th channel. And once it finished plotting, we can see the S wave in here. Not super strong, but we see a good S wave everywhere. If you look in terms of file structure, so it's the output, we see that it wrote these 15-second increment files in this case for the whole time. NetCDF files that we can just read with Extus or other NetCDF libraries, actually. Yeah. Okay. If there's no further questions, I'll be around the next 2 days as well. And then we can go on.
Yeah, so I propose a very short break, just 5 minutes.